Please title these notes Derivatives 3 Notes, Basic Rules, and write the little explanation that you see there. By the end of this lesson, you should be able to use the basic derivative rules for powers, sum, and difference to take derivatives. So, in a previous lesson, we were estimating the derivative of a function from its tangent line. And the problem is that estimating the derivative of a function from the slope of its tangent line on a graph is very imprecise. And a major achievement of calculus was to develop a set of rules so that if someone knows the equation of a function, they can find an equation that will give the exact value of the derivative of that function for any value of x. How they did it, I'm going to show you in just a second. So pause the video if you still need time to write this down and start it up again when you've finished writing. So what mathematicians wanted to do is they wanted to find the slope of this tangent line to this curve right here at this little dot. Unfortunately for them, they weren't able to find the change in y over change in x at a single dot because that dot, well, it was only one thing. There wasn't any up or over that could be done. It was infinitely small. But what they were able to do is they were able to find the slope of a line between two different points. So let's say over here. They could find the slope of this line just fine. The simple change in y over change in x. Now, what they discovered was that they could start bringing these 2 points closer together. So bringing that point B closer and closer and closer and closer to point A. And notice that as long as there are 2 points, we can continue to calculate that slope. You can see it over there on the right. And so what they were looking at is they were looking at the limit of this slope as B gets closer and closer and closer to A. So if we go back and we look at it, 1.7 goes 2, 3, and then after it gets to 3, it starts slowing down. And it keeps getting closer and closer and closer and closer to, if we were to actually be able to put those two dots right on top of each other, we're closer and closer and closer to 4. And while mathematicians of this time period didn't have fancy computer programs to calculate slopes for them, they did have a knowledge of limits, and they were able to find this limit as dot B gets closer and closer to dot A. What is the slope of that line getting closer and closer and closer to? Let's record what we just saw in the demonstration. So really how they did it, how they found the rules for the derivatives, is they took the limit of the slopes of the secant lines. The secant line just goes through 2 points where the tangent line just brushes at 1 point. Mathematicians found the limit of the slope of the secant line as the points on the function got closer and closer together. So moving from this first green line, this first blue line, finally to this purple line, notice that the slope of the line is getting closer and closer to the slope of the tangent line. Take a little bit to look at how mathematicians use the limit to find these rules. This is not something that we're going to work with in much detail at all during this particular unit, but when we do the limits unit, we're going to come back to this. And I just want you to see the origin of the rules that we're about to be working with, and also so you have a little appreciation for how much simpler these rules are than the original way that mathematicians needed to find limits and derivatives. So, let's look at this, finding general rules. So let's say that we have a function. Let's say this function is y equals x squared. It's actually y equals x squared plus 1, but that actually doesn't matter for now, so we'll just keep it simple. Actually, let's make it plus 1 just so you can see why it doesn't matter. Let's say there's some point x. We're going to try to find the slope of the tangent line at this point right here. And we also have some point A. It could be any number. This is just what we're going to use for the dot for the secant line. Now we've got the little line going through here. And we're going to have our change in y and our change in x for finding our slope. And we know that this point right here is a, and then a squared plus 1. That's the y value. We know that this point here is x, comma, x squared plus 1. We don't know what the value is for a, we don't know what the value is for x. We don't care, we're just trying to find a general rule. So we're saying our big question here is, what is the slope of the tangent line at x equals any number? Well, we know that slope is going to be change in y over change in x. And in this case, we find the change in y by simply subtracting this number, subtract that number. So that's x squared minus 1 minus a squared plus 1, whoops. And then the change in x is this x value minus that x value. So this is the slope of the secant line. Slope of the tangent line is the limit of that as this number, a, gets closer and closer to x. So notice up here, this negative is going to distribute here. So we've got positive 1, minus 1, so it goes away, it doesn't matter. We've just got x squared minus a squared over x minus a. Now we can see if we simply plug x in for a, do our substitution, we're going to get x squared minus x squared, which is 0, over x squared x minus x, which is also 0. So this is going to end up with the indeterminate form, 0 over 0, and we know that we can solve that by factoring. If you're a little rusty on this because it's been a summer since you've looked at it, don't worry, we're not going to be doing this in any detail. I just want to show you where it comes from. So we can factor notice that these two factors cancel right out. Limit as a approaches x of x plus a. Now we can just do substitution, except we're doing substitution, so we don't need to write the limit anymore. There we go. So that means that for this equation, y equals x squared plus 1, if we want to find what the derivative is, what the slope of the tangent line is at any value of x, we just take that value of x, multiply by 2, boom, that'll be our answer. After doing this many, 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 many times, mathematicians noticed a pattern. I'm going to write for you what they discovered. Over here we have the function, and over here we have the general equation for the slope of the tangent line. Remember, that's called the derivative. And so I'm going to write what the function was. We just had x squared. And we saw that the derivative was 2x. Well, mathematicians did the same thing for x cubed, and they found the derivative was 3x squared. Same thing for x to the 4th. Found the derivative was 4x to the 3rd. Same thing for x to the 5th. They found the derivative was 5x to the 4th. Etc., etc., etc. And so mathematicians looked at this, and they noticed that, lo and behold, there seemed to be a rule. If there was a function that was just x to the nth power, then all that seemed to be happening was that this exponent, became a coefficient. It was brought down in front there. And that 1 was subtracted from the exponent. And these patterns led to the derivative rules that are the focus of this unit. Notice how much easier this is than going all the way through the limit definition. So we're about to get into more detail of what all those rules are that mathematicians spent so long figuring out. Before that, though, a quick caution. These rules can only be used when a function is differentiable. Differentiable simply means you can take the derivative. It's sort of a self-fulfilling prophecy. But in general, what this really means the function must be continuous. That means don't lift your pencil. With no sharp turns. And no vertical tangent lines. Okay, let's move on to the actual rules themselves. Basic derivative rules. Dum, dum, dum. First thing to be aware of is just some notation. There are several different types of notation that actually mean the same thing. Let's say that we have an equation, y equals some function of x, or whatever. dy dx means the derivative of y with respect to x. So that means that we're going to use the rules that we're about to learn to just find something that's called the derivative of y with respect to x, and this is going to be what we get. So we're going to end up with dy dx, the derivative of y with respect to x, equals some equation. There's another way to say basically that exact same thing. Let's say that we have some equation f of x equals 3x plus 2. F prime of x, that little symbol is called a prime, just means the derivative of f of x. These two things are saying exactly the same thing, and our final answer will both be this equals whatever, this equals whatever that derivative ends up being. I want to contrast these two notations, though, with the third one. d dx of 3x plus 2. I'm going to number these so that we keep them a little clearer. This is different. This dy over dx is different from d over dx. Specifically, this is a command to take the derivative of what's to the right. So notice, we're going to have situations where we write dy dx equals something, f prime of x equals something, but we are not going to have situations where we have d dx equals something. This is active. It's telling us a command. We're going to take the derivative of what's right here. So be careful with those different notations. Now, finally, the basic rules. The first one is called the constant rule. And we're going to look at where these rules come from in the limits unit, but right now I just want you to be able to do the mechanics fluently. The power of calculus was that rather than making everyone do this the long way, it developed a series of shortcuts that could be used on their own independent of their origin. It's really important to learn the origin. Most classes do the origin first and then go into the rules. We're actually doing the rules first. I want you to be really fluent in how to use them, and then we're going to go back and look at where they came from in another unit. So the constant rule says, let's say that we are told to take the derivative of some constant c. So this is just a constant, some number. Not a variable, a number. If we are told to take the derivative of a number, that always equals 0. Every single time. So if I say take the derivative of 3, that equals 0. Here, I'll number these. If I say f of x equals 10, find the derivative of f of x. The derivative of a number is 0. If I have y equals 10, and I want to find the derivative of that function, 0. Anytime that we have a number, a constant, we're taking the derivative, it equals 0. And this actually makes quite a bit of sense if we look at graphing a constant function. A constant function just means like y equals 10 is just a flat line. The slope of this line, it's a flat line. The slope is always 0. So, try this one on your own. Take the derivative of square root of 36. This is just a number. The derivative of any constant number is 0. There we go. This is also true, incidentally, of numbers like pi or 1,964,000, whatever. As long as it's just a number, derivative is 0. Check. Once we get variables in there, things get a little more interesting. Next up is the power rule. That says that if we take the derivative of a variable to some power, so this is a variable x, n is just some number, what we're going to do is we're going to bring down this exponent, and then we're going to subtract 1 from the exponent. So, to give you an example, if we're told to take the derivative of x squared, I'm going to bring down the 2, and then I'm going to subtract 1 from the exponent. So 2 minus 1 is 1, or x to the first power, which is the same thing as 2x. if I'm told that I have function f of x equals x to the third, and I want to find the derivative, I'm going to bring down the exponent, subtract 1 from the exponent, and there we go. So try this one. Let's say we have the function y equals x to the fourth. I want you to find the derivative of that. Okay, what we do is we bring down the exponent, subtract 1, and there we go. Ta-da! This is really the main rule that's at the heart of a lot of taking the derivative. The other ones that we're going to go over are kind of just little variations on it. So I want to look for a second at why this makes sense. Let's say that we've got some function, let's say this is like x squared or something, and we're trying to find the derivative. Well, we know that right here the slope is 0, so I'm going to graph the slope just at that 0. So this is f of x, this is the derivative. Here it's a little negative, here it's even more negative, here it's a little positive, here it's even more positive. That x squared function turns into a linear or just an x function. Basically that's what we see here. This squared turned into a linear function. Likewise with something over here, if we started off with x to the third and we're finding the derivative, right here the slope is 0, here it's a little bit positive, here it's also about the same amount of positive, here it's really positive, here it's a really positive slope. And it forms that nice parabola x squared shape. You wouldn't necessarily see it immediately from doing all these graphs and see that pattern immediately, but if we look at it, it does line up with what we observe from the graphs. Basically, whenever we take a derivative, the power reduces by 1. X squared to x, x to the third to x squared. So the next one up is called the constant multiple rule. And what that says is it says that when we take the derivative of some constant times f of x, that's the same thing as just multiplying that constant times the derivative of f of x. Really all this says is that any number, any constant here, is just along for the ride when we do differentiation. So, for example, let's say we're taking the derivative of 3x squared. That's the same thing as doing 3 times the derivative of x squared. That 3 is just along for the ride. So we've got that 3, bring down the 2, and subtract 1 from the exponent. And there we go. So to give another example, let's say that f of x is 1 over 93 x to the third, and we want to find the derivative of f of x. This 1 over 93 is just along for the ride. What we're going to do is we're going to take the derivative here, bring down the 3, subtract 1 from the exponent, and there we go. Now we'll just multiply here. And that'll cancel to be 1 over 31 x squared. Any number in front, just along for the ride. Try this one on your own. Take the derivative, 6 x to the 5th. Okay, that 6 is just along for the ride. We bring down the 5, subtract 1 from the exponent, and there we go. The next rule is the sum and difference rules. Sum just means add, difference just means subtract. These are also kind of the same idea as the constant multiple rule. They're just saying things are along for the ride. So if we have a situation where we have two functions that are added together, and we're told to take the derivative of them. So let's say we have some function f of x plus g of x, and we're told to take the derivative. All that this rule says is that we take the derivative separately. Let me write that a little more neatly. Okay, I don't know if that counts as being neater, but derivative of f of x plus derivative of g of x. We just work with them separately. The same exact thing is true as subtraction. If we're subtracting f of x or we're subtracting g of x, same thing. So to give you an example of that, what we're looking at is, let's say that we're told to take the derivative of 3x squared plus 2x to the 4th. All we're going to do is take those two derivatives separately. Derivative of 3x squared plus the derivative of 2x to the 4th. When we do that, this 3 is along for the ride. Bring down the 2, subtract 1 from the exponent. Here this 2 is along for the ride. Bring down the 4, subtract 1 from the exponent. And there we go. If we have something like f of x equals x to the 5th minus 2x to the 4th, then when we're finding the derivative, we just treat them separately. 5x minus 1 from the exponent minus the 2, bring down the 4, 4 minus 1 is 3. Voila. So, I'd like you to do one on your own. Let's take the derivative of x to the 6th minus 7x to the 3rd. Pause the video now. Okay, we're just going to take the derivative separately. 6x, subtract 1 from the exponent. The 7 is along for the ride. We bring down the 3 and subtract 1 from the exponent. That gives us 6x to the 5th minus 21x squared. There is one special case that tends to trip people up that I want to go over really quickly. And this isn't any different from the stuff that we've been doing. It's just looking at what happens in this case. We're told to take the derivative of 3x. Now, we know that our power rule, is to take down the exponent, bring it down, and then subtract 1. But right here, we don't see an exponent. The thing to remember is that this is an invisible 1. So what we're doing here really is we're saying this is 3, bring down the 1, and then subtract 1 from the exponent. 3 times 1 is 3. 1 minus 1 is 0. And then remember, anything to the 0 power is just 1. So when you have a situation where you have 3x or 4x, or just sort of that linear function, then it's really important to be aware. This x is just kind of going to go away. And this makes a lot of sense because what we have is we have a linear function with a slope of 3. And when we take the derivative, we're asking what's the derivative of this curve? Well, the derivative of this curve, it doesn't matter what x is, it's always going to be 3. And that's why we see this. So either way that you think of it, just make sure that you aren't tripped up by that one. So if we see a similar example, we're just going to remember we bring down the 1, subtract 1 from the exponent. So this is now x to the 0, or just plain old 1, and it's 5 for the derivative. We can also think of that as it's a line with a slope of 5. The slope is always 5, so the derivative is 5. It doesn't matter what the value is for x. This is not something that's that hard to do. It's just really hard to remember it when you're sort of in the mode of doing other things. So let's do some final practice problems. Our checks for understanding. And I'd like you to do the following. I'd like you to take the derivative of 3x to the 4th minus 2x plus 1. Try that one on your own and restart the video when you're ready. Pause the video now. So the first thing to remember is the sum and difference rules, simply that when these are added and subtracted, we just treat them each separately. And we also remember that the variable here is just along for the ride. So we'll look first at this one. The 3 is along for the ride. Then we use the power rule, bring down the 4, subtract 1 from the exponent. Now here, this negative 2 is along for the ride. This is x to the 1st power. When we bring down the 1 and subtract 1, this is x to the 0, and it goes away. So it's just negative 2. And then the derivative of any number, that constant, that's 0. Another way to think about this is we could think about this as 1 times x to the 0 power. When we bring down that 0, anything times 0 is just 0. So there we go. So when we simplify this, we get 12x to the 3rd minus 2. Let's do one more and we'll be at the end of the notes. If f of x equals 6x to the 3rd minus, let's say, 5x plus 1 over the square root of 59. Let's find f prime of x. Pause the video now. Same as above, we do each one separately. This 6 is along for the ride. subtract 1 from the exponent. This -5 is along for the ride. We bring down the 1 and subtract 1 from the exponent, so this is x to the 0 and it goes away. This is 1 over square root of 59. It's just a constant, it's just a number. The derivative of a number is always 0, or we can think of this as x to the 0 power. Bring down the 0, it becomes 0. In any case, when we simplify all this, we're going to get 18x squared minus 5. That concludes the notes.